In this video, I will show you a bunch of reverse engineering tools. There are many reverse engineering tools in the world. So when you choose those tools, it's like you are going into a department store or say like a Best Buy. So you really need to choose the one that you like and I know that people have their own preference. So in this video, I'm going to just show you some of those tools that I personally like and I normally use. But reverse engineering tools are not only just them. There are a lot of more than this, and you are always welcome to explore by yourself. And also, if you happen to know any tools that you really like, I am also very happy to hear from you, and you're welcome to talk to me. So I like to divide all different kinds of reverse engineering tools into three categories: static tools, dynamic tools, and hybrid tools. Static tools are those tools that will read a binary statically without running or executing it. I usually just use readelf and opstomp to read the information about the ELF, the ELF binary. As you can see last time in our previous videos, I show you how I use readelf to read the ELF headers, program headers, section headers from ELF binary. And I also usually use opstomp to get some, like a disassembly information as well as help information from an ELF binary. There are some common features between readelf and opstomp, so it really depends on which one you like to use. Second, I'd like to recommend to you is hexdump. I know that hexdump is not commonly used if you do reverse engineering, but it's still very handy because it's very lightweight. And if you just want to get a byte or say several bytes from a binary, or if you want to just add the binary very quickly, you can use hexdump to do that. And third, again, is opstomp, but this way, as I said, it has different functionalities. If you want to read ELF information, you can use opstomp. But if you want to get disassembly, you can also use opstomp. And this is the part that readelf cannot achieve. Just keep in mind, sometimes the output that you get from opstomp can be wrong. And also, this is not just the case of opstomp. Other disassemblers also has this issue, which I will mention later. Dynamic tools are those via which you can run binary. I usually use GDB plus fancier plugins. There are a bunch of plugins. Here I also just call it derivatives because they are based on the original version of GDB. You can use PADA, which is, although outdated, still very useful. You can also use Jeff or PoundDBG, which are still actively maintained. And you may want to choose one of these three. And here is a nice article talking about the pros and cons for each of the derivative, and you can just choose whatever you like. And also, I would like to mention that these three tools are also very easy to install. I encourage you to install GDB and try out these three and choose the one that you like best. You may think that the static and dynamic tools that I have shown to you are quite old school. So here are some more advanced tools which combines static analysis and dynamic analysis together. They also provide you more advanced features, give you more information such as control flow graph, which I mentioned in our last in-class lab, as well as the compiler. The compiler means to show you the source code, which is analyzed from the binary. Also, there are many tools that combine the static and dynamic analysis together, such as a disassembler plus debugger. Here I'm showing you 5 very useful tools with their links. All of the tools are very popular and have been actively used in the community. IDA Pro is a disassembler plus debugger. Although it has the compiler feature, you have to pay for it. Hopper and GUIDRA come with the compiler feature and they're free. Binary Ninja and Radar 2, although they don't have the compiler, Their higher level representation of binary are also quite readable. I would recommend you to try them all and find the one that you like the best. You may wonder how those reverse engineering tools work. Why can they automatically generate those high-level information such as control flow graph or say disassembler code or even decompiler? So turns out that there are a lot of techniques behind the scene. Today, I'm not going to go over all of them because they're just like so many, but I'm going to show you two of them. One is disassemble and the other is function recovery. And if you're interested into those techniques, I encourage you to read those articles or ping me, and I'd like to share with you more information. So in terms of disassembly, as I mentioned when I talked about opsum, it may contain errors. So far, there's no disassembling technique that can disassemble any binary from any architecture 100% correct. People are still making effort on that. And there are two basic techniques that I would like to talk about: linear sweep and recursive traversal. So the way that linear sweep works is that it will start with the entry point of a program and disassemble from the first byte of the entry point. And it will do this gradually until it cannot find any other new instructions. This technique comes with multiple issues, and one of them is that it can mistake data as code. In some binaries, there might be data within the text section, which is the code section. However, linear sweep will also consider that as part of the code and disassemble it. Recursive traversal mitigates this problem by leveraging call instructions. So the way that it works is that it starts with the entry point and then keep disassembling until it hits a call instruction. Once it finds a call instruction, it will go to the destination of the call instruction and continue to disassemble over there. It will end until there's no more call instructions has been traversed. And this is why it's called recursive traversal, because every time a call is disassembled, it will go inside into the destination of the call. This method solves these linear sweep issues in misidentifying data as code. However, recursive traversal also has its own drawback, which is it may overlap some of the instructions. There are some of the code that may not be called by any of the other instructions or any of the functions. There might be that code inside binary. In this case, reverse traversal will not be able to touch it, not mention disassemble it. If you're interested in more details for these two techniques, you can check this link, which contains a paper talking about linear sweep and recursive traversal for disassembling binaries. Another technique that I would like to talk about is function recovery, or say unstripping. So for many binaries, when they're shipped to the users, you will not be able to see the symbol table. And this is because the binaries have been stripped using commands such as strip. The reason why people do that is because they want to save space from the binary so that the binary will be smaller. So they really want to remove those information, such as functions name, so that it will take reverse engineers much more effort to understand the semantics of functions. This stops evil reverse engineer to copy the code or to find bugs. It also stops benign reverse engineers such as us to help analyze a program. So we need to recover the function boundaries from a binary that was stripped. Turns out that function recovery is also open research. Because of compiler optimization, it's hard for us to really identify where the function starts and where the function ends. And more interestingly, there are functions actually overlapping. They use some code in common. And for more information, you can check this link, which is a paper talking about all the different possible layouts of functions, as well as a machine learning technique that identifies function in unstripped binaries. All this being said, my point is that automatic reverse engineering is considered hard and also remains open research. So when you use those reverse engineering tools, please keep in mind that the information that they provide to you can be wrong. So you have to be very cautious and independent when you analyze those binaries. And you don't want to heavily rely on the information comes from any tool. Okay, let's play with some tools together. I'm going to show you how to use those tools to analyze a binary. Let's take a look at this binary. So usually when I am given a binary, I will first check the format of the binary. So I would normally do file example.out so that I would know if this binary is something executable. And in this case, example.out is an F binary, so I know that I can run it. So next, I normally just run it, but I want to be very cautious about running a binary, especially a known binary. So usually I will have a virtual machine or a Dockerized environment for me to run a binary, making sure that the binary will not harm my own computer. Here I'm using a virtual machine, so I'm gonna just run it. Okay, so the binary is asking us for this book, Harry Potter and the Philosopher's Stone, how many pages in this book? And I'm gonna just type something random over there. And it says you're wrong. I have to keep going. Now I know, on a high level, what does this binary want? And sometimes you may just don't know, even though you run it, it may not output anything. So now is the time for us to take a look at this binary a little bit in depth. I usually try strings first, just get some random string from the binary. And sometimes the strings will give us some hint in terms of the context of the binary. So here in this case, we see something interesting. Book one's a name, right? And then how many pages is the book? This is the question that we got asked from the binary. And then it says, you're correct, your key is this. If you're doing a capture the flag, and if you're doing a reverse engineering, you may already get the answer, get the key, since the key has been stored in the binary. Now let's just keep going, assuming that the key is not really shown in the binary. So we keep looking at those strings. We found that there are also some of the, looks like the author's name, right? And also other Harry Potter's book's name. From this information, we know that this binary is about Harry Potter's book. Now's the time for us to use more advanced static analysis or dynamic analysis tool to analyze the binary. And in this case, I'm going to show you GUIDRA. GUIDRA is free. You can download it from guidra-sre.org. GUIDRA tool comes from the NSA's research directory. It is very useful, and also it has been actively maintained. Now I'm gonna start GUIDRA. I already downloaded it, and I just unzip it, and I can just run it. So when you open GUIDRA, it has some tip. I'll just close it. And then I will start from scratch. So I am going to create a new project. This is also something that you will need to do when you start a new project. So this is going to be a project that you work by yourself. It's going to be a not-shared project. And I'm going to put a name over here. Okay, now we have created a new project called week 4. And next, what I'm going to do is to import the binary into this project. In one project, you can open and analyze multiple binaries. Here, I'm going to open this example.out. It will ask you the format of the binary. This is L format, so just keep as what it is. Okay. It will pop up some information about the binary. You see there are alpha type, and then the alpha required library, which is libc in this case. And you can just click OK. And now we're back to this window again. And we double click it. It will pop up the window asking you if I would like to analyze it now. And yes. And another window. You don't have to take care of all of them, but making sure that you click the compiler parameter ID. Okay, and then we're going to start to analyze it. And this is sections in the binary. And next to it are the symbols of the binary. And you can click this out, and you can see all the functions. And this part is the data type of the binary, or those libraries related to the binary. In the middle, this is the disassembly of the binary. And if you click the functions such as main function, we'll be able to see the decompiled code. The decompiler code is very similar to source code, but it's still different. So let's take a look at the decompiled code. This part is the stack canary. We don't have to take care of stack canary at this point, and I will talk about stack canary when we go to the stack overflow and the stack protection part of our course. And let's just skip it, and we see function init with the argument local underscore 88. And here is the declaration of local underscore 88. Followed by that, there's a printf saying, this is the message that we get when we execute it. And after message, it asks you how many pages in the book. Next is a scan function. And it scans some value to argument local underscore 8c. And let's click this. We will be able to get the value coming from this particular field. It says a %sign followed by D. So this means this is a format string. And also we know from scanf that the first argument is a format string. So here we know that for this scanf statement, it reads an integer. Now I'm going to put a comment over here. It says that read an integer. We can also change the name and the type of this specific argument. So let's do a read type. And in this case, since it is actually %D, we know that the type of it is 3 character. And actually, after you change the type of it, it will automatically reflect in the function. Okay, and continue, we see that there is a comparison between local 20 and local 8c, which is read from scanf. And if the comparison is passed, then we're going to get the key. If the comparison is not passed, then it will say you're wrong and keep going. In the end, this is stack canary check again. And for now, let's not worry about it. So here, after you static analyze the binary, you will be able to see this string again, and you will know that the string is the key that we want from the binary. Now let's keep going, and assuming that we haven't seen this message. So what we really want to do is to be able to match these two. So we need to input the correct value of an integer so that the integer's value is equal to local underscore 20. Let's try to figure it out. What is the value for local underscore 20? So first, let's check the source code again. Local 20 is declared at the beginning of the function. However, there's no definition in the source code. So we know that there must be something happening inside this part of the code that implicitly configure the value for local underscore 20. Because reading source code cannot really help us now, let's just read the disassembly. So I saw that this is the comparison maps with the if statement, and edx points to local underscore 20. If you move mouse over there, again, like move mouse here, it will start to show you the stack of the function. And here we see that here is local 20. There is local underscore 88 below local 20. And there's local 10 that's above local 20. Because local 88 is next to 20 and also below 20, I'm guessing that maybe there's some operation related to local 88 that goes up into local 20. So let's take a look at the operations on local 88. Go back to the source code again. We found there is a function init taking local 88 as an argument. So now's the time for us to take a look at function init. I'm going to click it and go into it. This is a very interesting function because we see a lot of assignment over here. And again, remember this is variable local 88. So remember that what we are looking for is a local 20. The difference between local 20 and local 88 is hex 68. So let's take a look at this function and see if local 20, which is argument param 1 with offset of hex 68, has been assigned with any value. So if you look at the assembly, we found that this is the instruction that actually assign the value of hex df into this particular address. And here rax is equal to the argument, the first argument of function init, which is rdi. Because in the instruction, we see that param1 is passed to rbp plus local 10, and then rbp local 10 is passed to rax. So now we have another way to solve this challenge. We know that this place is assigned value with hex df. So the input that we need to give to the program is hex df. Now let's try it in terminal. First of all, let me get the actual integer for hex df. Okay, so that is 223. And I'm going to run the binary again. And we're correct. So this is another way for us to solve this challenge by statically analyzing the binary. Now I'm going to show you another way to solve this challenge. So let's go back to the main function. Here we found this is the critical point. We have put our input equal to the checking value. This if statement corresponds to the instruction of compare edx eax. This instruction is in the address of 100914. So in this approach, what we're going to do is we're going to mix our static analysis with dynamic analysis. So we use static analysis to figure out the critical instruction, and then we're going to use dynamic analysis to run the binary into this point and check the value of local underscore 20, which corresponds to register edx. Okay, I'm going to use GDB to run the program and then set a breakpoint at the instruction that we want. So I'm going to do GDB example.out. And then I'm going to set a breakpoint at the instruction. Let's turn back to GUIDRA and find the address of the instruction. So it's 100914. And let's make a breakpoint. 914. And start to run it. Here you'll see that actually this is a little bit weird. Why is the instruction is not the instruction that is saying over here? So the reason is that the binary itself is a PIE binary, means that it is independent of the address. So in theory, every time when this program is loaded and run, the base address that the memory image of the program is based on will be different. However, for GDB, it sets a fixed base address for x64 binary, which is this value. So what we really need to do is to set a breakpoint at this base address plus the offset of the instruction. And we can use opt_dump-d to take a look at the offset. So we go to the main function, and then we find that the instruction we want to stop at is at the offset of hex 914. So we change that to 914. Okay. We delete the first breakpoint and run. So now it's asking us how many pages in this book. We can put a random number over there again. And now we see that it stops at exactly what we want. And now we need to check the value of EDX. So we do P means to print, and EDX means to print the register of EDX. And we can get the value, which is equal to 223. In this case, we also managed to get the input. So now if we quit and then run with the value of 223, we can get the key. Now I'm going to show you one more approach to get the key. Let's look at the instruction of the if statement again. This is the instruction corresponding to the if statement. Followed by that is in conditional jump. It says that if EAX is not equal to EDX, it will jump to hex 926. What if we change this specific instruction? What if we change that so that it will not go to 926, but instead it will stay over here so that it will output the keys that we want? So what we should do? We can change the instruction instead of JNE, change that to JE. So let's find out what is the operating code that corresponds to JE. I just searched online and then I found the OP code for conditional jumps. JNE is 75 and JE is actually 74. So let's just change that particular byte from 75 to 74. And remember, the offset is 916, and this is in hex. We're going to just open this particular binary using Vim. And then we convert that to hex, and we locate the place of hex 916. So we want to find the 6th byte. So this is 10, 11, 12, 13, 14, 15, 16. Let's change that to 74. Okay, and then we convert it back to hex. We save it. Now let's run this again. So we're still typing a wrong value, but we change example out. And in the case, if we send in the wrong value, it will actually output the key because we changed the conditional jump. In summary, In this video, I show you a couple of tools, and I show you how to use these tools to solve the problem from example.out. Specifically, I'm showing you to solve example.out with 4 different kinds of approach. The first approach is to use strings to read the string out of example.out, and the second one is to use GUIDRA as a static analysis tool to find the embedded string. The third one is to use GUIDRA and GDB together to run the code and then check the runtime value of the register that are compared to the input. And the last is to use binary editing. So we change the actual control flow from the binary by changing the conditional jump so that even when we are giving it a wrong value, it will still output as it's correct. I hope that this video will help you in getting familiar with those binary analysis and reverse engineering tools, as well as to understand how to solve the challenges from our assignment.